Example 4, find the values of x for which each of the following functions is continuous. 4.1, right, if you look at it, it's f of x is a polynomial function. So f of x is a polynomial function. Therefore, it is continuous for every value of x, right? You can see that this comes from the first point there in the theory. We're looking now at 4.2. Your g of x is a rational function. That's the first point to note over here. G of x is a rational function. You can see that both the numerator and the denominator are polynomial functions. And if you look at the denominator, in this case, x squared plus 2, so the input squared plus 2, and this can never be 0 for all x an element of the real numbers. To convince yourself, you can draw the graph of, say, h of x is equal to x squared plus 2. The minimum value for the output is going to be 2, right? So therefore, your g of x is continuous for all x an element of the real numbers. No restriction in this case on for the denominator of the rational function. 4.3. Right, I'm going to leave this one for you to try on your own. You'll get the answer, this full solution in the PDF. So we go on to the next page. Consider f of x is equal to x squared minus x plus 1 on the closed interval from -1 to 4. Is there a value of x such that f of c is equal to 7? Right. So we're looking at this on the interval closed interval from -1 to 4, and we want to know whether there is a value c such that f evaluated at c is equal to 7. Right now, in this case, it's a quadratic function, so there are different ways of answering it, but you could be given a cubic or even a fourth degree polynomial equation. So the general way to approach this using continuity will be as follows. So the solution, you'll say f of x is a polynomial function, right? Now we know that it's going to be, since the polynomial function is continuous for all values of the input, for all x and element of the real numbers. But now we are looking at what happens to this function on the interval, uh, closed interval from -1 to 4. So f evaluated at -1, this gives us -1 squared minus -1 plus 1. So this is equal to 3. And if we take f evaluated at 4, this gives us 4 squared minus 4 plus 1. So that gives us an answer of 13. Now, if we look at the closed interval from -1 to 4, right? We know that f of -1 is 3, and f of 4 is 13. And we know that since we're dealing with a polynomial function, right, the graph, the function is continuous, right? So it means that somewhere in between, right, the output has to be somewhere between the outputs 3 and 13. The output has to be 7, right? So there's going to exist some value c where the output is 7, right? That's your c. So the diagram really illustrates to you what's going on. So since f is continuous on the closed interval from -1 to 4, there exists some c, an element of the open interval, right, between -1 and 4, such that f evaluated at that c is equal to 7. Right, number 6, you can try on your own. The solution will be on the PDF. Uh, Number 7, let f of x equal to the split function over there. You can see it's not defined at -3, and well, uh, at -3 you get a value of k, that's what they're calling it. And when x is not equal to -3, your f of x is equal to x squared minus 9 all divided by x plus 3. The question is, for which values of k will f be continuous at x is equal to 3? You must try this out using your three conditions for continuity, and you'll get the solution on the PDF.